this video, we'll be discussing phase change calculations. As you slowly heat a solid, you're going to increase its temperature until you get to a certain point where, even as you're adding more and more heat, the temperature doesn't change. This is the melting point of that solid. Any energy you're putting into it at this point does not raise the temperature of the substance, it is converting it from solid to liquid. Finally, once all of the solid is converted to liquid, any additional heat that's added is going to be raising the temperature of that liquid again until you hit the boiling point. Once you hit the boiling point, now all the heat that you're putting into it is actually not raising the temperature but converting it from a liquid to a gas. Once all the liquid's converted to gas, any additional heat increases the temperature of the vapor. So this is a lot like calorimetry, but with extra steps. The energy required to change the phase of a compound is what's known as enthalpy of phase change. Now in this case we have enthalpy of fusion, that's enthalpy of melting, and the enthalpy of vaporization, also known as boiling. Now what's interesting about these enthalpies is that if you go in the opposite direction, well, if you think about it, it's the same amount of energy, except instead of putting it into the substance to vaporize it, you are actually releasing it from the substance or the system in order to, in this case, condense it. So let's take a look at this to maybe simplify that concept a little bit. If we want to take water from solid to liquid, the enthalpy of fusion is 6.01 kilojoules per mole. If we want to freeze a mole of liquid, well, we're just going in the opposite direction. So the enthalpy of freezing is just the negative of the enthalpy of fusion. Now in this case, the negative sign means that this is an exothermic reaction. In order to solidify liquid into solid water, well, we have to release that energy from the system, the water in this case. Same thing goes for vaporization. We have to put energy into it, 44.7 kilojoules per mole, in order to convert 1 mole of liquid water to gaseous water. But if we want to condense it, it's the same amount of energy per mole, but now it is negative. It is exothermic. Now let's look at these values, these energies in kilojoules per mole. Let's compare them to the amount of energy required to raise the temperature of 1 mole of water from room temperature at 25 degrees Celsius to boiling at 100. This is just raising the temperature. For this we would use Q equals mc delta T. So we have we need a mass of 1 mole of water, that's 18.016 grams per mole, so 18.016 grams. We need the specific heat of water, 4.184 joules per gram degree Celsius, and we need the change in temperature. That's going to be an increase of 75 degrees Celsius. So by comparison, simply raising the temperature of water is only about 5.6 kilojoules per mole, whereas in order to vaporize it, to boil it, well, that's 44.7 kilojoules per mole. A lot more energy involved in many phase transitions, especially for something such as water, which has those hydrogen bonds, making it a lot more difficult to boil. So, for example, we want to calculate the energy required to convert 50 grams of water from ice at negative 15 degrees Celsius to steam at 110 degrees Celsius. Well, this involves a lot of steps. First, we have to heat the ice to the melting point, and we have to know the melting point of this substance. Thankfully, most people do. Then we have to melt the ice at that temperature, and we have to heat that resulting water to boiling, then we have to boil it, and then we have to heat the steam to the final temperature of 110 degrees Celsius. That's a lot of steps, and each one requires a slightly different equation. But in general, just 2 different equations. But we need to know the molecular weight of water. We need to know the specific heat of ice, liquid water, and gaseous water. They're all going to be different. And we need to know the enthalpy of fusion and the enthalpy of vaporization. So, step 1, Q1, we take 50 grams of water, multiply it times the specific heat of ice, and then multiply it times the change in temperature. Be careful. This entire process is going to be endothermic. All of these Q's are going to be positive. So don't just put in or plug in negative 15 degrees Celsius. It needs to be final temperature of 0, melting point, minus starting point, negative 15. This way we're going to get a positive value. Let's go ahead and heat this 50 grams of water from 0 to boiling. Process number 3. This time we have to use the specific heat of liquid water. Add that to our list. And then finally we're going to heat the steam. Again, this isn't everything. Now we have to take care of the melting and the boiling. Be very careful. In order to determine the heat of fusion, we need to know the number of moles of water. Enthalpies of fusion are given to us in kilojoules per mole, not kilojoules per gram. So we need to convert that 50 grams to moles by dividing it by the molecular weight. As you can see, there's a lot of energy involved there. And then finally, the boiling of the water. Again, you can do these in any order, as long as they're all in the same units. Convert all of these to joules. We could have converted everything to kilojoules, because that's probably what we're going to report in the end. And we add them up, and we get 164,274 joules, or 6 joules, or 164 kilojoules. Is close enough.